Hey everyone, it is March 22nd, 2018, time's about 11:55. It is Geo-Rant time, it's 33 degrees Fahrenheit out, and I'm sitting in the Jeep in a parking lot. It's not going anywhere, so I don't want to hear any snot about me driving and doing distracted stuff. But anyway, this Geo-Rant's going to be a little different. First, I'm going to use these as visual aids. I made them last night. But I'm going to talk about the process of mountain building, and then we're going to play with some numbers to see how far and how high a mountain range can get. You'll see what I mean in a second, but basically, as we know, how does the Earth move? All right, so you got two tectonic plates colliding. Eventually, what happens is one's going to move up and one's going to go under, like this, abduct back into the mantle, and we're concerned with this part up here. Specifically this part. So. Basically, back to that one. How does the Earth move? Well, there's really two things that are at play here to simplify it as much as I can. Tectonics and time. Okay? So, when a mountain range forms, we call that an orogeny or an orogenic event. Basically here, what I just showed you with my hands is I'm illustrating on the cards for you. 1 is the first one, 2 is the second one, 3 is the third one, and it's just a simplified cross-section, not to scale or anything, but to show you the process. And as you can see here, like you have arrows, this is the collision, this is the compression, and what that does is that drives one plate down under and pushes this one up and over, and that's what we're going to concern ourselves here with when we do our little mathematical modeling here. First, we're going to deal with the part that we're just going to deal with one axis. I mean, because even though this is a two-dimensional cross-section, this is really happening in 3 dimensions. You've got your x-axis here, your y-axis here, and your z-axis here. So the compression's happening along x, which is what we're going to go through here in a second. Just show you how that how that's going to override another plate or other units. And then we're going to get into the z. We're not concerned with the y because that would just be a long part of the mountain range. We're not going to deal with that part. So one plate thrusting over another plate. Let's just say it's at 5 millimeters per year, or about 0.2 inches per year. I am going to convert some of this metric into imperial for you, but not all of it. I only did the imperial part, so everyone is included. During a human lifespan, that isn't much. Like what I'm talking about here is you got the thrusting, this part. This hand here, how far is that going to get over this plate? All right, during a human lifespan, it's not that long. If we take our 5 millimeters per year and multiply it by 100 years, we get 500 millimeters. The years are going to cancel out, so you're just left with millimeters, which is 50 centimeters, or about 1.64 feet, or 1 foot 7 inches, 7.7 inches. All right. But what about on a geologic time scale? Let's stick with our 5 millimeters per year, okay? But let's calculate it for 2 million years instead of 100. So we do our 5 million years times our 2 million. I'm not going to use scientific notation at all here. I intentionally did that because I want people, who are like in 8th grade to be able to understand this and stuff. So we get 10 million millimeters, which converts to 1 million centimeters, which converts to 10 kilometers, or about 6.214 miles. Now, if our overthrust rate remains constant for that 2 million years, our overriding plate will move 10 kilometers over the underlying plate. So our overthrusting plate, our underlying plate, our overthrusting plate will move, from when it started, whatever point we decide to start running this calculation at, and over 2 million years, it'll run 10 kilometers. All right, that's what that's saying. But what if this process remains constant for longer, say 10 million years at the 5 millimeters per year? Well, we could figure this out the same way we figured out the last one, except for 2 million years we put 10 million years in, but there's no need to do that because 10 million divided by 2 million is 5. So, 10 million years divided by 2 million years is just 5. All the units would cancel. So we just need to multiply all those previous values we got by 5, and this is what we get. All right? So we get about 50 kilometers, or 31.070 miles. And this we see with the Pinocchian orogeny up north in the UP, where around where northern Wisconsin is and the Upper Peninsula, around where they meet, about 1.8-ish billion years ago, two continents collided, and you had an arc basin in between them, and that pushed a lot of sediments up and over. This would be the Michigamme Slate. So we do have kind of like, and that actually progressed about 30 miles inland. Well, assuming it's all thrust rate. But you got to remember too, when you get this collision and this thrusting over, these rocks here aren't just going to bend and deform. They're also going to fault, and they're going to start fracturing and faulting, and you're going to get like this kind of thing going, which I'm going to kind of show in a minute here. But there's other factors that can influence the rate at which mountain ranges grow. So we're going to do a problem like that. We have overthrusting, which I already went over. We have compression rate, height gain, and erosion. Okay, so as you're doing this overthrusting, there's other forces at part here. So it's not just like this gets deformed and slides over. This gets deformed and starts compressing, which is going to shorten your net gain, gain over the underlying plate. And as this builds up, we've got erosion trying to break it back down. So those are some of the other factors at play here. So we're going to do another one of these with these other factors. So basically, here's a cross-section of a thrust fault. It's not to scale or anything. And like I said, within continental collisions, you can get thrusting within the continental crust itself, and this shows you how those basic forces react. Here's your thrust fault right here. See, this part moves up relative to this part which has moved down. You get your height gain, you get your compression, and you've got erosion through wind and water and biological activity, if there was life on the land at the time, trying to knock this down. And this could be your baseline, it's your standard to measure this kind of relative movement with. Your baseline, you can pick whatever. You can pick the relative ground level, an average of the surrounding low-lying areas, or you could pick sea level, or if there's a lake in here, you could pick that. It doesn't matter, but that would basically be your baseline in this case right here. All right? So let's have some more fun with numbers. Let's say an orogenic event persists for about 15 million years, which is typical, but it could actually be a lot longer, and at a constant rate. So it's that the 15 million years is going to equal our t. So we have our compression, compression rate, which will equal c, which we have just assigned some numbers here for all this, so we can do some calculations, at 2 millimeters per year. Our overthrust rate, or O, is 9 millimeters per year. Our height gain, and when I say height, it also means tall, because I'm going to use that word as well, which is our H, which is equal to 3 millimeters per year, and our erosional rate E, I set it 2.3 millimeters per year, which is actually somewhat typical for erosion rates on higher lands, and it actually is kind of slightly under. But at the end of our 15 million years, how high would our mountain range be, and how far inland, otherwise overriding that other plate, or that underlying unit, how far inland will it reach from base level? And I just explained to you how we're talking about base level here. Well, we're trying to figure out our net overthrust and our net gain. So we need to use our ON for net overthrust, our HN for net gain. So our ON is going to be equal to our O minus our C. So there's the math on that. We get about 6 millimeters per year. Our net height gain is going to be our H minus our E, and we get 0.7 millimeters per year. Here's just some statistics on Mount Everest and where I pulled that from, and then I just converted to imperial for you here. Just keep that in mind. You don't need to memorize it or anything, because that's the last thing we're going to do here. So our ON is 6 millimeters per year, our HN is 0.7 millimeters per year, and our time, or T, is over a 15 million year period. So how do we calculate this? Net. That's because, like I said, you know, we're going to lose compression. I mean, we're going to lose our some of our overthrust due to compression, and we're going to lose some of our height gain due to erosion. All right, so it's a different, you know, we just calculated what that difference was. So now we just take our nets times our time. Okay, so here is our overthrust, net overthrust times our time, which is our 15 million years. And we get about 90 kilometers. Now when we do our net height gain, same thing, times our 15 million years, we get about 10.5, we actually get 10.5 kilometers. And you got to remember here, there's actually zeros after this. At this 10.5, I just reduced it to, I just got rid of them there because I'm going to put them back here at the very end. And I'm not really worrying too much about significant figures here in this scenario. So 10.5 kilometers, that's a tall mountain. So how much taller is our mountain than Mount Everest? Well, I did this little diagram. The height is to scale. Obviously, the width is not. And here's just the baseline that they're both compared to. So the top of Mount Everest is 8.848 kilometers. And the height of our mountain is 10.5 kilometers. And this is the difference in height between the two. Now, we could just physically measure this and get a rough estimate at this since the height is to scale on both of these. But let's do it mathematically. So our mountain is 10.5 kilometers, or 10.500 kilometers, if we draw out our significant figures, which is about 6.524 miles, which in this case is going to equal our MO. Mount Everest is equal to 8.48 kilometers, or 5.498 miles, or our ME. Now, I just did this, the reason why I did this in metric and imperials to see if my conversions were correct, to see if I get the same number. And here we do. We just divide our MO by our ME, and that's how many times MO is higher than our ME. So our mountain is higher than Everest. And we get the same number. So, you know, my conversions kind of checked out there. So, anyway, I just thought that this would be a little neat idea. Let me know if you want to see more stuff like this, and please remember to subscribe and like. If you want to use this video for educational purposes for someone else, feel free to. You don't need my permission. You have it now. But anyway, that is it for today, and I hope you all learned something.